Welcome to the first video on sampling distributions. This topic is actually a turning point in our class. So far, we've been mostly talking about values that are calculated to summarize data sets that have been collected from samples. We talked about how values such as the mean, median, or standard deviation can be calculated to get an overall picture of what the data looks like. However, we haven't gone into much detail about how a person uses the data from his or her sample to reach a conclusion about the entire population that the sample came from. At this point, we'll move away from discussing how to summarize a set of data, and we'll begin to cover the details of how a conclusion about an entire population is reached based on data from a sample. I think that people usually find this to be the most interesting part of statistics, because it's when we start to talk about how researchers answer questions about the world in which we live. Although the process of reaching a conclusion about an entire population based on data from a sample seems like it should be simple and straightforward, it actually isn't as straightforward as it seems. There are two major issues that people face when they use data from samples to reach conclusions about populations. The first issue is that a sample almost never provides perfectly accurate information about the entire population. For example, if 48% of the people in a sample say that they plan to vote for a certain candidate, that doesn't necessarily mean that exactly 48% of the population plans to vote for that candidate. The second issue is the fact that different samples will give different results. If a study is carried out with one sample, and then the study is repeated with a different sample, the results of the two studies will almost always be at least somewhat different. If you think about it, this makes perfect sense. After all, each sample is a different mixture of people. Now, these two issues might make it seem like it's not possible to reach a conclusion about a population based on data from a sample. These two issues might make it seem like collecting data from a sample is useless, because there's no guarantee that the results will be accurate. However, using data from a sample to reach a conclusion about a population isn't as useless as it seems. Although you can't prove something about a population with data from a sample, you can reach an inference about the population with a high level of confidence. That's because when research is done properly, the inferences that are reached about populations are correct more often than they're incorrect. In order to truly understand how it's possible to use data from a sample to reach an inference about an entire population, you need to have a good understanding of statistical theory. The goal of this lecture is to cover the theory that you need to understand before you can grasp the process of using data from a sample to reach an inference about an entire population. In later videos, we'll actually go through step-by-step examples of using data from samples to reach inferences about populations. However, in this video, we will just cover the theory that underlies the process of reaching an inference about a population with data from a sample. First, we need to understand the idea of sampling variability. Sampling variability is just the fact that different samples give different results. Here's an example of sampling variability. If I randomly select two different samples of JFK students, and I calculate the mean height of each sample, the means of the two samples probably won't be exactly the same. After all, one sample might include a larger number of shorter students, and one sample might include a larger number of taller students. One sample might have a mean of 61 inches, and one sample might have a mean of 69 inches. Now that we understand the idea of sampling variability, we need to understand the idea of a sampling distribution. In statistics, a sampling distribution is a collection of possible outcomes based on all possible samples of a certain size. It takes a little bit of imagination to be able to understand the idea of a sampling distribution, so I'm going to challenge you to use your imagination. Imagine that I'm planning to do a study to estimate the mean height of the JFK student population. I don't have enough time to record the heights of all JFK students, so I'm planning to randomly select 50 JFK students to be my sample. After I select my sample of 50 students, I will record the height of each person in my sample, and then I will calculate the mean height of my sample. Hopefully, the mean height of my sample will give me a rough idea of what the mean height of the entire population equals. Since I decided to do a random drawing of 50 people, I know that I'm definitely going to get 50 people in my sample. However, I have no idea which 50 people are going to be in my sample, The specific group of 50 people that ends up in my sample depends on chance. There are many possible combinations of 50 students that could be selected, even though only one of them will actually be selected. Each possible sample of 50 students that I might select has its own sample mean. Also, because of sampling variability, the possible samples don't all have the same sample mean. The shorter samples have lower sample means, and the taller samples have higher sample means. Since the different possible samples have different sample means, I really have no idea what my sample mean will equal. There are probably some samples out there that would give me a mean height of 61 inches, some samples that would give me a mean height of 64 inches, and some samples that would give me a mean of 67 inches. If I was able to actually list out the means of all of the possible samples of 50 students that might be selected in my study, I would have a really long list of sample means. That collection of sample means would be my sampling distribution. You might want to imagine a gumball machine in which each gumball includes a different group of 50 people. When I randomly select my sample of 50 JFK students, one of those gumballs will fall down and become my actual sample of 50 students. Each gumball in the machine has a sample mean written on the front of it. Once my gumball of 50 people falls down, the number that's on my gumball is my sample mean. It's my outcome. If I was able to look at the number on each gumball in the machine and then list out all of those numbers, that collection of numbers would be my sampling distribution. Basically, whenever a value is calculated with data from a random sample, the sampling distribution is just a collection of numbers that includes the value of the actual sample, along with the value of every other possible sample that might have been selected. At this point, you might be wondering, what if I wasn't calculating the mean of my sample? What if I was calculating some other value like the median of my sample or the standard deviation of my sample? Well, if I was calculating the median of my sample, then every possible sample that I might select would have its own median, and my sampling distribution would be the medians of all possible samples. If I was calculating the standard deviation of my sample, then every possible sample would have its own standard deviation, and my sampling distribution would be the standard deviations of all possible samples. Basically, whenever you calculate any type of value with data from a random sample, the sampling distribution includes the value of your actual sample along with the value of every other sample that could have been selected but was not actually selected. At this point, I wanted to mention that in statistics, it's important to understand the idea of a sampling distribution, but it's actually not necessary to be able to create sampling distributions. In this video, I will go through some exercises in which we create sampling distributions. However, I'll go through those exercises just because I think that they will help students understand the idea of a sampling distribution. I think that going through the steps of creating a sampling distribution makes the idea of a sampling distribution more concrete. Since it would be too difficult for us to create sampling distributions with data from large populations, we'll go through examples of creating sampling distributions with data from small populations. Also, I wanted to mention that in this video, we'll only focus on sampling distributions of means. We won't focus on sampling distributions of other types of values. We'll focus on means just to keep things simple for now. This will be our first example. We're going to pretend that these are the heights of 4 people in a small population. We're also going to pretend that I'm a researcher who's going to randomly select 2 people from this population and record their heights, and then calculate the mean of my sample to estimate the mean height of the entire population. If I'm planning to randomly select 2 people from this population, there are a few different possible samples that I might end up selecting. And let's look at those possible samples. If I randomly select 2 people from the population to be my sample, I might end up selecting person 1 and person 2. I might end up selecting person 1 and person 3. I might end up selecting persons 1 and 4. I might end up selecting persons 2 and 3. I might end up selecting persons 2 and 4. and I might end up selecting persons 3 and 4. So if I randomly select 2 people from this population to be my sample, these are the 6 possible samples. My actual sample is going to be one of these 6 possible samples. I'll show you how I was able to figure out what the 6 possible samples are. What I did first was I paired person 1 with every person under person 1. So first I paired person 1 and 2 together, and that was the first sample. Then I paired 1 and 3 together, and then I paired 1 and 4 together. At that point, I had no one left to pair with person 1, so I moved down to person 2. And then I paired person 2 with every person under person 2. So I paired 2 and 3 to be sample 4, and then I paired 2 and 4. At that point, I had no one left to pair with person 2, so I moved down to person 3, and I paired person 3 with everyone under person 3. The only person under person 3 is person 4, so 3 and 4 became my last sample. So basically what I did was 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and then 3, 4. And that gave me my 6 possible samples. Each possible sample of 2 people has its own sample mean. We can find the mean of each possible sample by adding the 2 numbers in the sample and dividing the total by 2. So these are the means of the different possible samples. Sample 1 has a mean of 55, sample 2 has a mean of 56, and so on. So what this is showing you is that the sample mean that I end up getting depends on which sample I end up selecting. If I end up selecting sample 1 and I collect data from sample 1, my sample mean will end up being 55. If I end up selecting sample 6 to be my sample and I collect data from sample 6, my sample mean will end up being 59. So this is just showing the idea of sampling variability. Different samples give different results. Also, some of these samples are more accurate than others. It turns out that the mean of this entire population equals 57. If we added these 4 heights and divided the total by 4, we would find out that the population mean is 57. So that means that sample 3 and sample 4 are perfectly accurate. If I end up selecting sample 3 or sample 4, then my sample mean will end up perfectly estimating the population mean. But if I end up getting sample 1, then my sample mean will underestimate the mean of the population. And if I end up getting sample 6, my sample mean will end up overestimating the mean of the population. So overall, we can see that samples 3 and 4 are the most accurate because their sample means actually equal the population mean. But sample 1 and sample 6 are the least accurate because those sample means are further away from the population mean. So overall, I would really like to get sample 3 or sample 4, and I really wouldn't like to get sample 1 or sample 6. But as a researcher, I have to realize that the sample that I end up getting depends on chance. So these 6 sample means that we see in here make up the sampling distribution for the sample size of 2. We could list them out over here. So these 6 numbers in this column are just the means of all possible samples of 2 people that could be chosen from this population. So 55 is right here, 56 is right here, and so on. So these 6 sample means make up the entire sampling distribution for the sample size of 2. Now what if I wasn't selecting a sample of 2 people from the population? What if I was selecting a sample of 3 people from the population? Well then I would end up getting one of the possible samples of 3 people. And we can look at what those possible samples are. These right here are the 4 possible samples of 3 people that could be chosen from the population. So if I randomly select 3 people from this population to be my sample, I'm going to end up getting one of these 4 possible samples. My actual sample will end up being one of these 4 possible samples. I'll explain to you how I was able to figure out what the possible samples are. Each time I wrote out a different sample of 3 people, I just left out one person from the population. So when I wrote out sample 1, I left out person 4. When I wrote out sample 2, I left out person 3. When I wrote out sample 3, I left out person 2. And when I wrote out sample 4, I left out person 1. So if you want to write out all possible samples of 3 people from a population of 4 people, all you have to do is just leave out one person each time. It's pretty straightforward. And if we calculate the mean of each possible sample of 3 people, and then we write out those 4 sample means over here, those 4 sample means will make up the sampling distribution for the sample size of 3. So let's do that. We can calculate each sample mean by just adding the 3 numbers in the sample and dividing the total by 3. So if you add these 3 numbers and divide the total by 3, you get 56. If you add these 3 numbers and divide the total by 3, you get 56.67. And these are the other 2 sample means. And now that we know what the 4 sample means are, we'll just list them out over here. And these 4 sample means make up the sampling distribution for the sample size of 3, because these are just the means of all possible samples of 3 people that could be selected from this population. And you might have already noticed that these 4 sample means are packed in closer to the population mean than the 6 sample means that we had in our last example. And if you notice that, you would be correct, because when you go up to a bigger sample size, the sampling distribution moves in closer toward the population mean, and it becomes less spread out. And that makes sense because larger samples are more accurate than smaller samples. At this point, I wanted to discuss the mean and standard deviation of a sampling distribution. A sampling distribution is really just a collection of numbers. So just like any collection of numbers, a sampling distribution has a mean and standard deviation of its own. It turns out that the mean of a sampling distribution is always equal to the mean of the population. And I'll actually demonstrate this point right now. Let's go back to this example where we were looking at the sampling distribution for the sample size of 2. If we add these 4 numbers over here in the population and divide the total by 4, we'll get the mean of the population. If we add the 6 sample means of the sampling distribution and divide the total by 6, we'll get the mean of the sampling distribution. And if we did that, we would see that the 2 means would come out to the same number. So the mean of the population equals the mean of the sampling distribution. These 2 means have to come out to the same number. And we can see here that they did come out to the same number. They both came out to 57. So the mean of the individual people in the population always equals the mean of the sample means in the sampling distribution. This symbol, which is the Greek letter mu, is a symbol for population mean. So that's why I use this symbol over here to refer to the mean of the population numbers. This symbol right here, which is mu x bar, is actually the symbol for the mean of a sampling distribution of sample means. The reason why the symbol is mu x bar is because it's the mean of the sample means. I would think about it that way. This slide is just a visual of how the mean of the population equals the mean of the sampling distribution. In this figure right here, we can see the heights of the 4 population members, and we can see that the mean of the population is at the center of the population. These 2 people are below the mean of the population, and these 2 people are above the mean of the population. Over here in this figure, we can see the 6 sample means and the sampling distribution, and we can see that the mean of the sampling distribution, mu x bar, is at the center of the sampling distribution, and these sample means down here underestimate the population mean, and these sample means up here overestimate the population mean. Also, like I said earlier, these 2 sample means are the most accurate because they equal the population mean of 57, and this sample mean of 55 and this sample mean of 59 are the least accurate because they're the furthest away from the population mean of 57. So as a researcher, I would really like to get one of these 2 samples, and I really wouldn't like to get this sample or this sample. But remember, the sample that I get depends on chance. So as a researcher, I have to hope that I get an accurate sample. Let's now look at one other example of how the mean of the population equals the mean of the sampling distribution. We already know that the mean of these 4 people in the population is 57. If you add their 4 heights and divide the total by 4, it comes out to 57. And what we're going to look at right now is how the mean of these 4 sample means also equals 57. If we add the 4 sample means in this sampling distribution and divide the total by 4, we get 57. So the point that I'm making here is that the mean of the sampling distribution equals the mean of the population no matter what sample size you're dealing with. It doesn't matter if the sample size is 2 or 3 or any other sample size. So here's another visual of how the mean of the population equals the mean of the sampling distribution. This is just the same figure we looked at earlier. It's the heights of the 4 people in the population, and the population mean of 57 is at the center. Over here, these 4 sample means are the means of all of the possible samples of 3 people that could be selected. And at the center, we have the mean of the sampling distribution, which is the same thing as the population mean. And we can see that down here, these sample means underestimate the population mean of 57, and these sample means overestimate the population mean of 57. And one point that you've probably already noticed is that these 4 sample means in this sampling distribution are packed in closer to the population mean compared to the sample means in the other sampling distribution with a sample size of only 2. Because when we were looking at the other sampling distribution with a sample size of 2, we had a sample mean down at 55 and a sample mean all the way up at 59. But now all of our sample means are between 56 and 58. All of our sample means are pretty close to the population mean of 57. So like I said, when the sample size goes up, the sample means move in closer to the population mean. That's just because bigger samples are more accurate and more dependable. So here we have a visual that shows us that the 4 individual people in the population have the most dispersion. Their individual heights have the most dispersion. The means of the possible samples of 2 people have less dispersion. They're closer together than the individuals are. And the means of the possible samples of 3 people have even less dispersion. So as you go from When you go from each value being one person to each value being two people to each value being three people, the values move in closer and closer to the center. They have less and less dispersion, like we see in this diagram. So the main point behind this diagram is that larger samples are more accurate than smaller samples. If you want to estimate the mean of a population, you're better off with a larger sample than with a smaller sample. Because if you use a larger sample, your sample mean is likely to fall closer to the population mean that you're estimating. So all three of these distributions have the same mean. They all have a mean of 57, which we can see here. We can see that all three of these are pretty much centered at 57, but they don't all have the same dispersion. Like I said, the left one has the most dispersion, the middle one has less, and the right one has the least. Since we're already talking about the dispersion of a sampling distribution, that leads us into our next concept. We were talking earlier about how the sampling distribution is really just a list of numbers, so it has a mean and standard deviation of its own. The mean of the sampling distribution is equal to the mean of the population, and the standard deviation of the sampling distribution has a special name called the standard error. So if you calculate the standard deviation of a sampling distribution, you would call it the standard error of the sampling distribution, even though it really is just a standard deviation. So this is kind of just an example of statistical terminology. We talked about how the standard deviation is a measure of dispersion. So the standard error is a value that measures the dispersion between the values in a sampling distribution. If we took the 6 sample means in the sampling distribution for the sample size of 2, and we calculated the standard deviation of those 6 numbers, the answer would be called the standard error, even though it really is just a standard deviation. Also, if we took the 4 sample means in the sampling distribution for the sample size of 3, and we calculated the standard deviation of those 4 numbers, the answer would be called the standard error, even though it really is just a standard deviation. And you can probably guess that the sampling distribution for the sample size of 2 had a bigger standard error, and the sampling distribution for the sample size of 3 had a smaller standard error. And you would be correct, because the 6 sample means in the first sampling distribution were more spread out, and the 4 sample means in the second sampling distribution were less spread out. So the first sampling distribution would have the larger standard error. The main point that I'm trying to make is that when the sample size goes up, the standard error goes down. So when we go from the n equals 2 sampling distribution to the n equals 3 sampling distribution, the standard error goes down because the sample means move in closer together and become more accurate. So one way to think about the standard error is that if you're using a small sample size, the standard error will be larger because the possible samples are more spread out and their sample means are less accurate. The sample means tend to be further from the population mean. And if you're using a larger sample size, the standard error will be smaller because the possible samples will be more accurate. Their sample means will be closer to the population mean. So when you use a larger sample size, the standard error goes down, and that's a good thing because it means that the possible samples that you're drawing from have more accurate sample means. Now that you understand the idea of the standard error, we'll go through some examples of calculating standard errors by hand. I'll actually show you 2 different methods for calculating the standard error. The first method that I'll show you isn't very practical, at least not in a real study, but I want to show it to you just because I think it'll make it clear that the standard error really is just the standard deviation of a sampling distribution. After I show you that method, I'll show you the formula that can actually be used in a real study to calculate the standard error. In our first example, we'll calculate the standard error of the sampling distribution that we looked at earlier, which was the means of all possible samples of 2 people that could be selected from that population of 4 people. These are just the 6 sample means that we looked at earlier. Each one was the mean of a combination of 2 people. If we want to calculate the standard error of this sampling distribution, we just need to follow the standard deviation formula, because after all, the standard error really is just a standard deviation. So if we go through the steps and we calculate the standard deviation of these 6 numbers, the answer will be called a standard error. The first step in calculating a standard deviation is calculating the mean of the values. We can get the mean of the values by adding the 6 values and dividing the total by 6. We're dividing by 6 because there are 6 of them. So the mean of this sampling distribution equals 57. And remember, 57 is also the mean of the population, because the mean of the population always equals the mean of the sampling distribution. The second step in calculating a standard deviation is to subtract each value by the mean. That's what we'll do right here. So we're just subtracting each value in our sampling distribution by the mean of 57. And this will give us deviations. 55 minus 57 is negative 2. 56 minus 57 is negative 1. These 2 equal 0. 58 minus 57 is 1, and 59 minus 57 is 2. Each of these deviations is just showing us how far each sample mean falls below or above the population mean. So this sample mean of 55 is 2 below the population mean of 57, so it has a deviation of negative 2. This sample mean of 58 is 1 above the population mean of 57, so it has a deviation of 1. So now we understand what these deviations are. The next step in our formula is to square each of the deviations. You have to multiply each deviation by itself. So remember that we're just following the standard deviation formula, and one of the steps in the standard deviation formula is multiplying each deviation by itself. So that's what we're doing right now. Negative 2 times negative 2 is 4. Negative 1 times negative 1 is 1. These 2 equal 0. 1 times 1 is 1, and 2 times 2 is 4. Now that we have our square deviation column, we need to do the next step in the standard deviation formula, which is finding the mean of the square deviations. To do that, we add the square deviation column, and we divide by the number of squared deviations. And there are 6 of them, so we divide by 6. In an earlier video, I told you that when the data comes from a sample, you divide by n minus 1 instead of n. But that's not what we're doing here, because we're actually not finding the standard deviation of a sample. We're finding the standard deviation of a sampling distribution. We're finding the standard deviation of the means of all possible samples. So in this situation, we don't use n minus 1. We only use n minus 1 when we're finding the standard deviation of the people inside of a particular sample. So we divide by 6, and then we get the mean of the squared deviations. Remember, it's called the variance. You don't have to worry about that, but it's called the variance. And the square root of the variance is the standard deviation. So 1.29 is the standard deviation of this sampling distribution. So this sampling distribution over here has a standard error of 1.29. And you might be wondering what that's telling us. Well, what that's telling us is that each of these 6 sample means is on average 1.29 away from the population mean. So so on average, these sample means are 1.29 off target. It's just the average. It's really just the average distance from each sample mean to the population mean that's being estimated. So like I said, on average, each sample mean is 1.29 off target. And it's our standard error. Now what if we wanted to find the standard error of our other sampling distribution, which was the means of all possible samples of 3 people? We would follow the same formula. We would just follow the standard deviation formula. The first step is finding the mean of the values. There's 4 of them, so we add them and divide by 4 to get the mean, which is 57. We subtract each value by the mean to get our deviations. Once we get the deviations, we square them. We multiply each deviation by itself to get squared deviations. Then we find the mean of the squared deviations. We do that by adding the 4 squared deviations and dividing the total by 4. We're dividing by 4 because there's 4 of them. So this is just the mean of the squared deviation column. And if we find the square root of that, we get our standard deviation, which in this case is called the standard error. So this sampling distribution has a standard error of only 0.7. So the standard error did go down when our sample size went up. What this standard error is saying is that on average, these sample means are 0.7 off target from the population mean. Back when we were using a sample size of 2, we noticed that on average, the possible samples were 1.29 off target. But now that we're dealing with a sample size of 3, the possible samples are only 0.7 off target on average. So when the sample size goes up, the standard error goes down, and that just means that the possible samples are more on target, they're more accurate on average. And we're almost at the end of this video. I just wanted to show you a shortcut formula for finding the standard error. And it's this formula right here. I just have to explain what each of these symbols are. This might look complicated, but there's really only 3 symbols in here. This Greek letter, which is sigma, is the standard deviation of the population. It's the standard deviation of the individuals in the population. Little n is the sample size, the number of people in the sample, and capital N is the population size, which is the number of people in the population. So if we want to use this formula to get the standard error, the first step is finding the standard deviation of the population. And then after that, the rest of the steps are pretty straightforward because we just have to know the population size and sample size, and then we can plug them in. So here's our first example. Well, before we go through an example, I'll go through the steps with you. If you want to use the standard error formula, first you have to calculate the standard deviation of the population. And then after that, you can just go ahead and finish using the formula, like I said. So here's our first example. We're actually going to use the standard error formula to find the standard error for all possible samples of 2 people that could be selected from this population of 4 people. In this situation, I'm randomly selecting 2 people out of the 4 people to be my sample, and I want to know what the standard error of the sampling distribution equals. So the first step is just calculating the standard deviation of the 4 people in the population, which is these 4 people right here. So I calculate the standard deviation of their 4 heights, just following the regular standard deviation formula. I divide by 4 because it's an entire population and not a sample. The mean of the squared deviations, or the variance, comes out to 5, and the square root of the variance is the standard deviation. So the individuals in the population have a standard deviation of 2.24. In other words, the population standard deviation is 2.24. That's sigma. And since we know what the population standard deviation is, we can plug in all of the numbers into the standard error formula to get the standard error. So we know that our population size is 4, because I was taking a sample of 2 people from a population of 4. We want to find the standard error for the sample size of 2. In other words, we want to find the standard error for all possible samples of 2 people. So our sample size is 2. So now I plugged in all of these numbers. The population standard deviation, 2.24, which is what we found together. The population size of 4, and the sample size of 2. So on top we have 4 minus 2, and on the bottom we just have the population size of 4 minus 1. That's just a part of the formula. Now we can go through the steps of figuring this out. So first we have to do 4 minus 2, that's 2. Then on the bottom, 4 minus 1, that's 3. Then under the fraction, we divide 2 by 3. 2 divided by 3 is 0.67. Then we just find the square root of 0.67. It's 0.82. Just put this under a square root sign and it comes out to 0.82. Now we should divide this fraction. Divide the numerator by the denominator. 2.24 divided by 1.41 is 1.59. So when you divide this fraction, it comes out to this, 1.59. Now we just have 2 numbers that we have to multiply. 1.59 times 0.82 is 1.3. So that's the standard error. And this formula is a different way of getting the standard error than what we did earlier. The first way we did it was by actually calculating the means of all possible samples and then finding the standard deviation of the sample means. But if we use this other method that I just showed you, we don't actually have to calculate the means of all possible samples. So let me show you how we would have done this using the old method, or the method that we used the first time. So if I wanted to use the old method to find the standard error for all possible samples of 2 people, I would have to actually sort this population out into all possible samples of 2 people. There would be 6 of them. Then I would have to calculate the mean of each possible sample, and I would have 6 sample means. and then I would just calculate the standard deviation of those 6 numbers. That's the old method. But I think this new method that I showed you can be used without having to actually sort out the population into all possible samples. One major advantage of using the standard error formula instead of the method that we used the first time is that when you use a standard error formula, you don't have to sort the population into all possible samples and then calculate the mean of each sample. You can probably guess that in a real study, when you're taking a sample from a big population, it's not possible to calculate the means of all possible samples. So in an actual study, you would have to use the standard error formula because it wouldn't even be possible to sort out the population into all possible samples. I'll show you an example of how this formula could be used in a real study. Imagine that I'm randomly selecting 50 JFK students to be my sample, and I'm recording the heights of the 50 people, and I'm calculating the mean of my sample to estimate the mean of the entire university. And in my study, I want to calculate the standard error to be able to get an idea of how far off target my sample mean is likely to be. If I know what the standard deviation of the heights in the JFK population equals, I can plug that into the formula right here. And if I know the number of people in the JFK population, I can plug that in right here. And right here, I'll just plug in my sample size of 50. And then this formula would actually give me the standard error for all possible samples of 50 students that I might end up selecting from the population. And then that standard error would tell me how far off target my sample mean is likely to be, or how much accuracy I can expect. Now you might be wondering, what would you do if you don't know the population standard deviation or the population size? Well, that's actually an issue that we'll get into in the next video. Let's think about what it would mean if I calculated the standard error in my study and it came out to 5.4. I'm just throwing that number out there. What that would tell me is that when I randomly select my sample of 50 students from the JFK population, there are many different possible samples of 50 students that could be selected, and each possible sample has its own sample mean, and the standard deviation of all of those sample means equals 5.4. Now, why would I care that the standard deviation of all of those sample means is 5.4? I would care because that means that even though some of the sample means are more accurate than others, the average distance from each sample mean to the population mean is 5.4. That means that in my study, I can reasonably expect my sample mean to be about 5.4 off from the population mean. I can't be certain that my sample mean will be 5.4 off from the population mean, but I can reasonably expect for that to happen. This is the last slide that I'll show you in this video. This slide is just showing a side-by-side comparison of the two methods for finding the standard error. On this slide, I'm showing you the work for finding the standard error for the sample size of 2 and the sample size of 3 using both methods. If I wanted to find the standard error for the sample size of 2, one way I could do it is by sorting the population into all possible samples of 2, and then calculating the mean of each sample, like I did here, and then calculating the standard deviation of all of the sample means in the sampling distribution. If I did it that way, I would see that the standard error for the sample size of 2 equals 1.3. Another way for me to find the standard error for the sample size of 2 would be to use the standard error formula. If I wanted to use the standard error formula, the first step would be to find the standard deviation of the population. I could find the standard deviation of the population by doing this work right here. After doing all of this work, I can see that the standard deviation of the 4 people in the population is 2.24. Once I know what the population standard deviation is, I can just plug it into the standard error formula right here. And I would also plug in the population size of 4 and the sample size of 2. The sample size is 2 because I'm trying to find the standard error for the sample size of 2. After I go through all of this work right here, I would get 1.3 as my answer. So both methods would tell me that the standard error for the sample size of 2 is 1.3. Now what if I wanted to find the standard error for the sample size of 3? One way to do it would be to sort out the population into all possible samples of 3 people and calculate the mean of each sample, and then list out the sample means, like I did here, and then go through all of this work of calculating the standard deviation of all of the 4 sample means. If I went through all of that work, I would see that the standard error for the sample size of 3 equals 0.7. But another way for me to find the standard error for the sample size of 3 would be to just use the standard error formula. If I wanted to use a standard error formula for the sample size of 3, I would pretty much do the same work that I did here. The only difference is I would change the sample size of 2 to 3. And then I would go through all of this work over again, and then I would end up getting 0.7 as my answer. I would get the same answer that I would have had if I had gone through all of this other work and found the standard error using this longer method. So basically, there's 2 ways to find the standard error. You can sort out the population into all possible samples of your sample size, calculate the mean of each sample, and then calculate the standard deviation of all of the sample means. Or you can just use the standard error formula. And like I said earlier, in an actual study, you would need to use the standard error formula because in an actual study, when you're sampling from a big population, it's not possible to actually collect data from all possible samples and then calculate the mean of each possible sample. I wanted to go through a couple other examples of creating sampling distributions. This time we'll use a population that's a little bit bigger. In this example, we're looking at the exam scores of 72 students who are in the same class. This is a small population of students. The mean exam score of the class is 80. If we added the 72 exam scores and divided the total by 72, the answer would come out to 80. We're going to pretend that I'm a researcher who wants to know what the mean exam score of the class equals. Since I don't have time to survey all 72 students in the population, I'm going to take a random sample of 3 students, record their exam scores, and then use the mean of my sample to estimate the mean of the entire class. In my situation, the sampling distribution would include the means of all possible samples of 3 students. How would I create that sampling distribution if I wanted to actually create it? Well, to create that sampling distribution, I would need to calculate the means of all possible samples of 3 students that could be selected from this population. That would take me a long time because there's many possible samples of 3 students that could be selected from this population. However, let's take a look at some of the possible samples that are in the sampling distribution. Here's one possible sample of 3 students that could be selected. This sample has a mean of 81.7. We can plot that sample mean down here on this number line. I should have plotted it as an X bar because it's a sample mean, but we'll just pretend that this X is an X bar. Here's another possible sample of 3 students that could be selected. This sample has a mean of 74. We can plot that sample mean down on the number line as well. Hopefully this demonstration is starting to show you the idea of sampling variability. We can already see from this demonstration how different samples have different sample means. One important point about sampling distributions is that the possible samples overlap. The three people in these blue circles are a separate sample of three people, even though they include some of the people who are also in the brown circles. And we can see that this blue sample has a mean of 75.3. We can plot that sample mean down on the number line also. If I'm planning to randomly select 3 students from this population, any one of these possible samples could end up being my actual sample. Remember that if I randomly select 3 students from this population, the sample that I end up getting depends on chance. Any one of them could be chosen. We're starting to see that most of the possible samples in the sampling distribution have a sample mean within a certain range of the population mean of 80. In other words, most of these possible samples are at least fairly accurate. However, we can see that the different samples have different sample means. And we can see that some of the sample means are further away from the population mean than others. In other words, the sample means aren't all equally accurate. As a researcher, I have to hope that I get one of the sample means that's close to the population mean, and I have to hope that I don't get an extreme sample with a sample mean far below the population mean or far above the population mean. If I get a sample with a sample mean way down here, I'll end up underestimating the mean of the class by quite a bit. And if I end up getting a sample with a sample mean way out here, I'll end up overestimating the mean of the class by quite a bit. But if I get a sample with a sample mean somewhere near the population mean of 80, then I'll end up estimating the population mean pretty accurately. At this point, this graph is only showing part of the sampling distribution, because it isn't showing the mean of every possible sample of 3 people. If we kept going, and we plotted the mean of every possible sample of 3 people, then this graph would show the entire sampling distribution. Let's take a look at some other possible samples of 3 students. The students in the green circles are another possible sample of 3 students that could be chosen, and those 3 students have their own sample mean. Their sample mean is 89.3, which is out there. It's above the population mean. These students in the orange circles are another possible sample of 3 students that could be chosen, and they have their own sample mean, which is 86.7. We're just looking at a few other possible samples. Whenever 2 different possible samples have the same sample mean, their 2 sample means are just stacked above each other. So these 2 samples both had the same sample mean. They both had a sample mean of about 82. So those 2 sample means are stacked above each other. And now we have 3 samples that all have the same sample mean. So these 3 sample means are all stacked above each other. Once the sample means begin to stack above each other, that's when the sample means begin to form a shape that we can see in this graph. And if we kept going, these sample means would keep building up to form a shape. And then once we actually calculated the mean of every possible sample of 3 students, we would have the complete sampling distribution for the sample size of 3. And that sampling distribution would have a certain shape. Notice how most of the possible samples have a sample mean within a certain range of the population mean. The population mean is the center point of the sampling distribution right here, and the As you go further away from the population mean, you start to see fewer and fewer sample means. Let's now look at an example with a different sample size. If I wanted to randomly select a sample of 10 students from this population and calculate the mean of those 10 students, then my sample would be a member of a different sampling distribution. My sample would be a member of the sampling distribution of all possible samples of 10 students. Let's take a moment to look at some of the possible samples of 10 students that could be selected from this population. Here's one possible sample of 10 students, and these 10 students have a sample mean. Their sample mean is 80.2. If we add their 10 exam scores and divide the total by 10, we get a sample mean of 80.2. We can put that sample mean down here on this number line. I should have probably, well, actually I think this is pretty close to 80.2, so I think I did put it in about the right spot. Here's another possible sample of 10 students in the green circles, and these 10 students will have their own sample mean. If we add their 10 exam scores and divide the total by 10, we get a sample mean of 81. So right here, we have the mean of the 10 students in the orange circles, and right here we have the mean of the 10 students in the green circles. Those two samples are two different possible samples of 10 students that could be chosen from this population. Now let's look at a different possible sample of 10 students that could be chosen. The students in the blue circles are another possible sample of 10 that could be chosen, and they have their own sample mean. If you add their 10 exam scores and divide the total by 10, their sample mean comes out to 82.2, which is about right there. You might have noticed already that the possible samples of 10 students have sample means that are clustered in closer to the population mean. And you might have noticed that the possible samples of 3 students that we looked at earlier had sample means that were spread out further away from the population mean. That's why larger samples are considered to be more dependable and more accurate. If you calculate a sample mean with a large sample, your sample mean is likely to be closer to the population mean, because when you select a large sample from a population, most of the possible samples that you're drawing from have sample means that are pretty close to the population mean. A smaller sample is more likely to give you an extreme sample that highly underestimates or highly overestimates the population mean. So if we moved on and we kept looking at more possible samples of 10 students, we would still see that most of the possible samples have sample means close to the population mean. And if we actually took the time to calculate the mean of every possible sample of 10 students, and we plotted those sample means in this graph, we would see the complete sampling distribution for the sample size of 10. Before we move on from this example, I wanted to mention that there's actually a different sampling distribution for every possible sample size. So far, we've only looked at the sampling distribution for the sample size of 3 and the sampling distribution for the sample size of 10. However, since there's 72 people in this population, each possible sample size between 1 and 72 has its own sampling distribution. If we wanted to, we could look at all 72 sampling distributions. We could look at the means of all possible samples of 2 people, the means of all possible samples of 3 people, the means of all possible samples of 4 people, and so on. At this point, I wanted to explain one of the most important concepts in the topic of sampling distributions. This concept is called the central limit theorem. The central limit theorem allows us to predict the shape of a sampling distribution of sample means without having to create the sampling distribution. In other words, the central limit theorem allows us to predict the shape of a sampling distribution without having to actually calculate the mean of every possible sample that could be selected from the population. According to the central limit theorem, the shape of a sampling distribution of sample means is predictable based on the shape of the population and the sample size. The central limit theorem makes a couple of important points. First, it says that if the population is normal, then the sampling distribution is always normal. In other words, if the individuals in the population follow a normal distribution, and you randomly select a sample from that population, and you calculate the mean of your sample, the means of all of the possible samples that could be selected will follow a normal distribution, regardless of what sample size you're using. The other point that the central limit theorem makes is that if the population is skewed, then the sampling distribution is skewed, just like the population when a small sample size is used, but is roughly normal when a large sample size is used. In this case, large generally means 30 or larger. In other words, if the individuals in a population have a skewed shape, and you randomly select a small sample from that population, and you calculate the mean of your sample, the possible samples that you're drawing from will have sample means that follow a skewed shape that looks just like the population. However, if a population is skewed and you randomly select a large sample from that population and you calculate the mean of your sample, then the possible samples that you're drawing from will have sample means that follow a roughly normal distribution, even though the population that the sample is coming from is skewed. And this concept is difficult to understand at first because it seems really abstract, but I'll show you a simulation website that I think will make this idea more clear. This is a simulation website that lets me randomly select a sample from a population of 18,000 people. In this box right here, we can see the sleep time of each of the 18,000 people in the population. In this column, we see the ID number of each person in the population. And over here, we see each person's sleep time. So it looks like person 1 sleeps 6.5 hours per night, person 2 sleeps 6 hours per night, and person 3 also sleeps 6 hours per night. And this goes all the way down to 18,000 because there's 18,000 people in the population. Down here, we can see that the sleep times of the 18,000 people follow a roughly normal distribution. The mean, or the average, sleep time of the population is 8, or to be exact, it's 8.001. So if we added all 18,000 sleep times and divided the total by 18,000, it would come out to 8.001. We can see that that population mean of 8 is right at the center of the population, right here. Because when a population follows a normal distribution, the mean is at the center. Actually, the mean, median, and mode are all at the center of the distribution. So over here, we can see the people in the population who were below average and who were getting less than 8 hours of sleep per night. And down here, we can see the really sleep-deprived people who were getting less than 4 hours per night. Up here, we can see the people in the population who were above average, who were getting more than 8 hours of sleep per night. And down here, we see the people who were getting a lot of sleep. For example, these people are getting 12 hours of sleep up here. So now that we understand what this screen is showing, we'll actually randomly select a sample from this population. The first thing I need to do is click right here where it says Show Sampling Options. And I can pick a sample size. I can type whatever number I want in here, but I'll use a sample size of 10. And So when I click on Draw Samples, it's going to give me one sample of 10 people. It's going to randomly draw 10 people from this population. And then it's going to collect data from those 10 people, and it's going to show their 10 sleep times inside this box right here. So here's my sample of 10 people. These are their ID numbers, and these are their sleep times. So this is just randomly selected 10 people from the 18,000 people over here. We can see that my sample of 10 people has a mean sleep time of 8.025. So if we added their 10 sleep times and divided the total by 10, we would get 8.025. This is just showing that the sample mean is at the center of the sample. The sample mean is at the center of the 10 people in the sample, which makes sense. Over here, we can see the sample mean of 8.025 plotted as a single block above this number line. So this is just one block in the sampling distribution of all possible samples of 10 people that could be selected from this population. Let's randomly select another sample of 10 people. So we're repeating our study. So now it's randomly selected a different group of 10 people from this population, and it's recorded their sleep times. My new sample has a mean of 7.7. So if you added these 10 sleep times and divided the total by 10, it would come out to 7.7. So my new sample is a little bit more sleep deprived than my first sample because my second sample has a lower sample mean. And one thing I haven't shown you yet is that if you look over here, it actually highlights the 10 people in the sample inside of the population that they came from. So this person who's sleeping 9 hours is probably right here somewhere. It's probably this person. This person who's getting 6.25 hours, that person is probably that person right there. Now let's select a different sample of 10 people and calculate the new sample mean. This time, the sample mean came out to 8.425. So my third group of 10 people has a mean of 8.425, and it plotted that sample mean right there. So each time it takes a new sample from the population and calculates the sample mean, it plots that new sample mean on this graph right here. Each sample mean that's calculated is shown as a block. So this was the mean of sample 1, this was the mean of sample 2, and this was the mean of sample 3. Also, when you go and click on another sample, it actually shows you the 10 people that were in that sample. So these were the 10 people from sample 1, these were the 10 people in sample 2, and these were the 10 people in sample 3. And if you click on this sample mean down here, you can see that these 10 people are a little bit lower. They're getting a little bit less sleep. And you can see that these 10 people over here are kind of getting more sleep, especially because of this person up here. That's why these 10 people had the lower mean, and these 10 people had the higher mean. Now I can keep drawing more and more samples of 10 people, and it'll keep calculating the mean of each sample. And each new sample mean will be plotted as a new block on the number line. And it tells me how many samples I've selected so far. So far I've calculated the means of 62 different samples. So these are the 62 sample means that I've calculated. And each sample mean is the mean of a different group of 10 people who come from this population right here. This group of 10 people has a pretty high sample mean. this sample of 10 people has a mean of 9.1, and if we look at the 10 people over here, we can kind of see why their sample mean is so high. It's mostly because of these three extreme people who are bringing up the mean of the sample. And the most important point I wanted to make here is that if we actually calculated the mean of every possible sample of 10 people that could be chosen in this population and plotted all of those sample means on this graph, those sample means would follow a normal distribution right here. This shape would be normal. The reason why is because if the population is normal, the sampling distribution is always normal. And I don't think this will let me calculate the mean of every possible sample because there's too many possible combinations. But if I calculate the means of 10,000 different samples and I plot those 10,000 sample means in here, I'll end up seeing a shape that's pretty close to the shape of the entire sampling distribution. So it's gonna draw 10,000 samples one at a time. Each sample will have 10 people, and it's going to calculate the mean of each sample. So it's going to plot 10,000 different sample means down here. So we can see that it is roughly normal. And if I click inside of here, I can actually look at the 10 people inside each of the samples. So let's look at this number 8 right here. Each building block that's stacked above 8 right here is just the mean of a different group of 10 people, and it just happens to be that all of those different samples all have a mean of 8. So here is one group of people with a mean of 8. Here's a different group of people with a mean of 8, and here's another group of people with a mean of 8. They're just all stacked above each other. Down here, we see all of the possible samples that have a mean of 7. And up here, we see all of the possible samples that have a mean of 9. But it's important for us to realize that every sample mean that's plotted in here is the mean of a different combination of 10 people. Now, what if I wasn't using a sample size of 10? What if I was using a sample size of 30? Well, if I click on Draw Samples, it'll let me draw samples of 30. So what I'm doing right now is each time I click on this icon right here, it draws 30 people from this population randomly, and it calculates the mean of the sample. And so far I've done it 4 times. So this is the mean of one group of 30 people. This is the mean of a different group of 30. This is the mean of a different group of 30. And here's the mean of one other group of 30. Now, the sampling distribution for the sample size of 30 includes the means of all possible samples of 30 that could be chosen from this population. If I was able to actually calculate the means of all possible samples of 30 that could be chosen from the population and plot all of those sample means on here, that distribution would be the sampling distribution for the sample size of 30. And a probably can't do that because there's too many possible samples, but just like last time, I'll take 10,000 samples, and I think that'll give us a shape that's pretty close to the sampling distribution. So what this is going to do is it's going to select 10,000 samples of 30 people one at a time. So it's going to take 30, it's going to take 30 again, and it's going to take 30 again, over and over. And each time it does that, it's going to calculate the mean of the sample. So it's going to randomly select 30, calculate the sample mean, randomly select 30 more, calculate the sample mean, and it's going to do that 10,000 times. And each time it does that, it's going to plot the new sample mean on here. So there's going to be 10,000 sample means on here. And that's going to be, the shape is going to be pretty close to the shape of the sampling distribution for the sample size of 30. It might just take it a second to do this, because it has to do it 10,000 times. Oh, there it is. So it's plotted the 10,000 sample means on here. So this is just showing 10,000 different sample means. And each of those sample means is the mean of a different group of 30 people that was selected from this population. So down here we have samples with really low sample means, and up here we have samples with really high sample means. So down here would be a group of 30 people who's more sleep deprived, so these 30 people have a low average. Here we have a group of 30 people that's more well rested, and so this sample has a high average. And in here we have all of the groups of 30 people that have more medium averages close to the population mean. So these samples are less accurate. They don't represent the population as well, and these samples are also less accurate. And the more accurate samples are in the middle, because in the middle we have the samples that have sample means closer to the population mean. But the most important point I wanted to make here is that the shape of these sample means is normal, just like the shape of the population. So far we've looked at two different sampling distributions. We looked at the sampling distribution for the sample size of 10, and now we've looked at the sampling distribution for the sample size of 30. The sampling distribution for the sample size of 10 was just the means of all possible samples of 10 people, and the sampling distribution for the sample size of 30 is just the means of all possible samples of 30 people. And we've seen that both sampling distributions have a normal shape. So far we've demonstrated the first point of the central limit theorem, which is that if the population is normal, if the individuals in the population follow a normal curve, then the sampling distribution is always normal, regardless of what sample size you're dealing with. It doesn't matter if the sample size is 10, 30, or any other number. Now at this point I want to demonstrate the other point of the central limit theorem, which talks about what happens when the population is skewed. So right here, I can change the population to a skewed population. So here we have a population that's positively skewed. Most of the people in the population are at the low end, so we have a lot more sleep-deprived people. And you see fewer and fewer people when you go up to these higher sleep times. So I said the population is positively skewed. And let's try to randomly select a sample of 10 people from this population and calculate the mean of the sample. So it's going to draw 10 people and calculate the mean of the sample. The sample mean came out to 8.675. That's the mean of these 10 selected people, and it plotted the sample mean right here. Now let's take 10 other people and calculate the mean of our new sample. This sample mean came out to 7.6. So this is the mean of sample 1, this is the mean of sample 2. And if we do this over and over again, what you'll start to notice is that since the population is positively skewed, our 10 people are typically coming from the low end of the population down here. That's happening simply because there's a lot of people to draw from down here and not as many people to draw from down here. So since our 10 people are typically coming from the low end of the population, our sample mean is typically coming out to a low number down here. So if we keep doing this over and over again, the sample means are going to pile up toward the low end. The sample means are going to keep piling up at the low end, and they're not going to pile up as much at the high end, because we're going to be getting a lot more sleep-deprived samples and a lot fewer well-rested samples. So the sampling distribution right here is going to end up looking like the population. It's going to be positively skewed because, like I said, the sample means will pile up here at this end more quickly than they do over at this end. Let's take a look at that. And we're not going to really see the shape until we have lots of samples in here. So far we have about 94 sample means in our sampling distribution. Now I'll try to take 10,000, just like I did before. So there's going to be 10,000 sample means in the distribution. It just takes it a second because it's calculating the means of so many samples. So we can see that this sampling distribution is positively skewed, just like the population. It's positively skewed just like the individuals in the population. It's not as skewed as the population is, but it's still somewhat positively skewed. So this shape does kind of look similar to this shape. And this is just demonstrating this part of the central limit theorem, because I said that if the population is skewed and you take a small sample from the population, like a sample size of 10, then the sampling distribution is skewed just like the population. And I also told you that if you take a larger sample, like 30, then the sampling distribution will be roughly normal, even though the samples are coming from a skewed population. So let's do that. Now I'll randomly select some samples one at a time. When I click on Draw Samples, it's going to give me one sample of 30 people, and it's going to calculate the mean of the sample. So the 30 people that it selected have a sample mean of 7.592, and it plotted the sample mean down here. If I click on Draw Samples again, it's going to take one new sample of 30 people and calculate the sample mean. So this time the sample mean came out to 8.275, and it plotted the mean of the second sample right here. If we keep doing this over and over again, what we're going to notice is that each time a sample is selected, the sample is still going to include a lot of people from the low end of the population. That's because there's a lot of people to draw from down here. But since we're using a larger sample size of 30, there's going to be a few more higher people mixed in. And those higher people will bring up the sample mean so that the sample means don't pile up at the low end as much as they did before. And that's going to make the sample means follow a normal distribution instead of the skewed shape that we saw with a smaller sample size. So like right here, notice how these higher people who were mixed in to the sample are bringing up the sample mean. So now the sample means are going to follow a normal distribution, even though the population that the samples are coming from is skewed. That's the last point that the central limit theorem makes. Slide, which is just a summary of the central limit theorem. The central limit theorem says that if the individuals in the population follow a normal distribution, the sampling distribution of sample means is always normal, regardless of what sample size you're dealing with. In the demonstration that we just did, we saw that when the population followed a normal distribution, the sampling distribution of sample means was normal with a sample size of 10 and with a sample size of 30. So the shape of the sampling distribution was always normal when the sample size was small and when the sample size was large. We also saw that when the individuals in the population were positively skewed, like this curve right here, the sampling distribution of sample means was also skewed when we used a small sample size of 10, and the sampling distribution of sample means was roughly normal when we used a sample size of 30. So overall, when the population is normal, the sampling distribution is always normal, regardless of the sample size, and when the population is skewed, the sampling distribution is skewed, just like the population, when the sample size is small, but the sampling distribution of sample means is roughly normal when the sample size is generally 30 or larger. At this point, you might be wondering why the central limit theorem is an important idea. In later videos, we'll talk more about its importance, but for right now, I wanted to give you a quick preview of why it's important. Basically, if you're taking a sample from a normal population, or if you're taking a sample of at least 30 from a skewed population, and you know that the sampling distribution is normal, then it's possible to predict how far your sample mean is likely to fall from the population mean. That's because when the sampling distribution is normal, sample means further away from the population mean at the center are less and less likely. We can see that when the sampling distribution is normal, the sample means further from the population mean become less and less likely as the normal curve goes down in both directions. If you're taking a small sample from a skewed population, and you know that the sampling distribution is skewed, then it's not as easy to predict how far your sample mean is likely to fall from the population mean. That's because when the sampling distribution is skewed, sample means at one end of the population mean are more likely than sample means on the other end of the population mean. That's because the sampling distribution is skewed or lopsided in one direction. So basically, if you're randomly selecting a sample from a population, and you're calculating the mean of your sample to estimate the mean of the population, you want to either be sampling from a normal population, or if you're not sure whether the population is normal, you want to be taking a sample of at least 30. That way, you'll know that the sampling distribution is normal, and you'll be able to make a prediction about how far your sample mean is likely to fall from the population mean that you're estimating.